Alright, so yesterday's lesson was on kind of a general intro to limits, so we kind of have an idea of what a limit is. Um, it's a value that we're approaching from the left and right. It's got to be the same point, um, and it doesn't necessarily have to equal that value, right? It's just got to be getting really, really close to it. Okay. Um, and if your function is continuous, then it's always just the same as the value there, right? And that's nothing too crazy. But a lot of times we run across situations where we have holes or vertical asymptotes or some issue where we have to do a little bit of algebra, a little bit of math to figure out what the limit is, right? Today is talking about all the different laws or rules that go with limit operations and things like that, and how we can solve different types of limits. You probably might have seen this lesson before, and if you have, that's great. If not, that's great too. Okay. So the first slide here, I'm just going to quickly go over some limit laws. And some of these are a little obvious, or you might have done them already, but I want to skim through this. But this is kind of your list to have, and we'll kind of go from there. All right. So it says let's assume that we have the limit of f of x as x is approaching a, and the limit of g of x as x approaches a. So we got two separate functions as x is approaching a. Okay. Um, the first three, the first three you've probably kind of seen before, and it's kind of makes sense. It's kind of like a almost distributive property if you think of it that way. Um, the limit of f of x plus g of x can be separated into two individual limits. Same thing if we were subtracting the two functions. If I had the limit of one function subtract another function, I can split it up into two separate functions. Okay. And if I have a constant times a function, all right, in a limit, then I can just take that c value out. Okay, that's the same thing as doing the constant times the limit of the function as x approaches a. So again, I think those first three are pretty straightforward, and even the fourth one here is again I think pretty straightforward. If I have two functions multiplying by each other, all right, if I'm taking the limit of two functions multiplying by each other, I can split those again into two separate limits. Okay, and the same thing for number 5. Okay, if I have two functions dividing by each other, I can separate those into two limits being divided. All right, so those are kind of your operations with limits at the beginning there. Plus, minus, multiply, divide. They can all pretty much be split up, and you can kind of distribute that limit if you want to think of it that way. Okay. Number 6 here, it says the limit. So if I have the limit of f of x raised to a power of n as x approaches a, all right, if it's being raised to the function, you can pretty much take it out to where the entire limit is being raised to that power. So it's like you can factor out that power, if that makes sense, where n has to be a positive integer. Okay. I think the next one kind of just makes sense to me. I mean, number 7 is saying like the limit of a number as x approaches a is just that number. I mean, that's just because it's a constant, right? Let's say the constant is a 2. Okay. Well, yeah. I mean, obviously, as I'm approaching a from the left and right, it's just the same number no matter what. So yeah, it's always going to equal that constant too. I think that's just pretty straightforward. Okay. Um, yeah. 9 and 10, or yeah, 8 and 9. I'm sorry. Well, 8, 9, and 10, I guess. Um, I don't even see those as properties. I mean, those are just kind of obvious facts to me. If I have the limit of x as x is approaching a, you just plug in a. You're approaching a. If you plug in a, it's going to be a to the n. You plug in a, it's going to be the nth root of a. Um, and that's just kind of always the first idea with limits is if you can plug in the value, if it's equal to the value of the function, then you're golden, you're set. So I don't even view those as any separate properties. I think those are just more common sense. And then lastly, if you're taking the nth root of a function when you're taking the limit, you can take the nth root of the entire limit. You can kind of bring that out. That's kind of similar to the same property as number which number was that? Number 6 above. Okay, those kind of are the same. So just gotta keep those in mind, and use those to help you with these next problems here. This little warm up here, I'm telling you what each of these individual limits are equaling, and then you're just practicing the properties below. So I'm gonna let you try that on your own for the sake of time and for this video, and we're gonna do that together in class. But see if you can do it on your own. I mean, it's nothing too crazy. It's just using some basic limit operations for that one. And it's the same thing for this problem here. I'm going to let you try this problem as well. It's the same as the last problem, but instead of me explicitly giving you the limit at the beginning of the problem, you have to figure out the limit yourself from the graph. So that's kind of practicing a little bit of stuff from yesterday as well. So try this on your own, see what you can do. And this is where we'll kind of pick up tomorrow. All right, but right now I want to talk about, well, limits, right? And how to do algebraic properties with limits to be able to solve them, because sometimes it's not going to be as easy as just being able to plug the value in, okay? Well, let's kind of start through the process here. Let's kind of go over like kind of what I keep in mind, what I try to do first, and kind of what I work down the list to do, okay? First thing I like to do is the direct substitution property, okay? That literally means plug it in, okay? So if a polynomial or a rational function, if f is a polynomial or rational function and a is in the domain of f, then if this is true, life is great. It says that the limit of f of x as x approaches a is just equal to f of a. That's just saying that you have a continuous function. And if you have a continuous function, the limit's super easy to find. It's just the same as the value. Like, for instance, I mean, if that's my function, okay, like right here at a, all right, the limit is equal to the value because it's continuous. So this would be true in this situation. And if you had that situation, life is great. So my suggestion always, before you're trying to do anything crazy, always see if the limit just exists. If the limit exists, if you can plug the value in, good. If not, then you might have to do a little bit of math. Okay. So for instance, okay, so let's try like number 1. Okay. I always try to do this property first. Like I always try to plug in the number, and if I get an actual value, I'm done. It just means it's continuous to that point. We're great. So if I plug 1 into this, it's 1 cubed minus 1 over 1 squared minus 1. You get 0 over 0, and that's no good. You can't do 0 divided by 0. So that means that and you can even see that it makes the denominator especially 0. You can see that that value doesn't exist in the original problem. So f of a doesn't exist, which means this isn't necessarily true. But just because the value doesn't exist doesn't mean that the limit doesn't exist, right? That's when you have to do a little bit of algebraic properties and see if there's like a hole there instead or what's going on, okay? So let's kind of see what's happening. Just looking at this, you probably can see a factor, like you can factor the top and factor the bottom. The bottom is so I'm gonna rewrite this. Limit as x approaches 1. The bottom is actually just a difference of squares, so that's x minus 1, x plus 1. And the top is a difference of cubes, which we remember is the cube roots of each, okay? And on the inside of the other parentheses, it's going to be the first value squared. All right, change the sign, and then it's going to be a times b. Originally I said 2ab, but it's a times b, so that's just x. And then always positive, the last one squared is 1. Okay. So you see that now x minus 1 and x minus 1 now cancel out. So what I'm left with is the limit as x is approaching 1 of x squared plus x plus 1 all over x plus 1. So now if I were to plug 1 into that, if I plug 1 into that, I'm going to get 1 squared plus 1 is 3 on top, and 1 plus 1 and on bottom is 2. So the limit is 3/2. That must mean that like at the value, like I have no idea what this function looks like, and you're welcome to graph it, some type of rational. I don't really care what the other pieces look like, but all I know is that 3/2, or I'm sorry, at at 1 on my graph, the value doesn't exist, but the limit does. So that must mean at 1, I have a hole at like 3/2. I don't again, I don't know what's going on to the left and right at that point, but I know they are meeting up at 3/2. Okay? There's a hole there, but the value doesn't exist. So that happens if you can cross that value out. So that's kind of what I like to do there. All right. So take a second, see if you can think about that. Always try to factor out something on top and bottom, and if that hole factors out, life is good. All right, now as we go on to number 2, and as we go through the rest of these examples, I got a few examples through number 6 on the other slide. We're just going to be discussing different types of limits that you may pop across, different types of strategies you can do to solve these, and just stuff you might see. So maybe we might do all 6 in the video, or we'll see how time goes, but whatever we don't do, we'll do in class tomorrow. So like for instance, look at number 2. Okay. We get the square root of 1 plus h minus 1 over h. Now, I always start by trying to plug in 0 and see if that works. If you plug 0 into that, obviously you see that the denominator is 0, so it does not exist. So the value doesn't exist. There's either a hole there or an asymptote, but we need to see if the limit does. So we need to see if we can cancel out that denominator to see if it's a hole, and if it's a hole, the limit does exist. If it's an asymptote, that's not necessarily true. Okay? Now, how can I cross this out? Well, what I notice on top is I have the square root of something minus like a constant or some number or whatever. I'm thinking, all right, that looks an awful lot like something I can do with maybe a conjugate pair. Like, so if you ever see a situation like this, conjugate pair is never a bad thing to try. So why don't we multiply the top by 1 plus h plus 1, and the bottom by the square root of 1 plus h plus 1. See if that does anything. Okay. So I'm going to do this times this. Okay. And remember, that's just going to be foiling. First, outer, inner, last, that kind of stuff. And if I do that, the square roots cancel out for the first term, so that's just going to be 1 plus h. All right. And then the middle terms with a conjugate pair, remember, are going to cancel out. That's negative root 1 plus h and positive root 1 plus h. Those just go ahead and cancel, so I'm not going to write that down. And then negative 1 plus positive, or negative 1 times positive 1 is just negative 1. Okay. And then on bottom, I'm just going to leave it as h times the square root of 1 plus h plus 1. Okay. It's still a limit. Technically, like on the AP exam, like, yeah, you got to make sure you write that limit every single time or they'll count it wrong. Okay? Now, if you notice on top, so we'll go ahead and rewrite it again, limit h approaches 0. If you notice on top, the 1 and the negative 1 cancel out, so I'm left with h over h times the square root of 1 plus h plus 1. And now you might notice that the h's cancel out. So that thing that made the denominator 0 is now gone. So that must have been that h was at 0 was a hole and not a vertical asymptote. So now we're left with the limit as h is approaching 0 of 1 over the square root of 1 plus h plus 1. Okay. So now if I plug 0 into the new simplified function, it might work out. Okay. So plug 0 into that, that's going to be 1 over the square root of 1 plus 1, because h is just 0 now, which equals 1/2. So in this case, the limit is 1/2. That must mean that they both meet at 1/2 from left and right. The value is not equal to 1/2, but the limit is. So it must be a little hole there. Okay. Cool. Alright, so take you a second and pause the video and write down, these steps I give you for doing algebraic limits. So if you're not able to plug it in or able to look at a graph or something, these are the steps I always take and try to consider when doing algebraic limits. Okay, so I want to just go through them real quick and explain it. You can pause the video and write them down. But the first thing I try to do is evaluate. I try to plug it in. I always try to see if it's continuous, and I can just plug it in and life works out. If that's the case, great. But most times when I'm doing these problems, it's not going to work. So I'm going to have to do some type of factoring, okay? So the idea is that hopefully that point is actually a hole. And if it's a hole, it'll be able to factor out and cross out, and I'll be able to plug in the value at the end, okay? So I'm going to factor. You saw in the last example, I did conjugate pairs. That's if I ever see like a binomial with a square root. And this is if I have two terms here. Difference of squares you already saw me do, and sum and difference of cubes. So those are ways to factor rationals and try to cross out your whole. Or you might want to do trinomials or grouping. So some type of factoring that can cross out something on top and bottom of a fraction that'll get rid of that whole and make it to where you can plug it in. Okay. So you already saw me talk about multiplying by the conjugate. That's if you see a square root with a binomial. Always try that. Another helpful tip is to, if you have multiple fractions, try to add those fractions to one fraction. So you can try to do something like in the previous step with you have the factoring. Okay. Limit laws that we talked about at the beginning. Number 6 we're about to talk about here. Sometimes it's not going to factor out. Sometimes like it's just going to be a vertical asymptote. Okay. Well, a vertical asymptote doesn't necessarily mean the limit doesn't exist, so we have to show a proof by using test points. I'll show that here in a minute. We're also going to do an example of an absolute value problem. Those happen with limits all the time. In that case, you have to look at two separate equations. We discussed in a previous video that absolute value is just a piecewise function, and we'll explain that here again in a minute. And then also complex fractions. I mean, I would solve complex fractions the same exact way as I would simplify them, and then try to do some previous rules above. Okay. So, again, pause the video, write those down, but take you a minute, and we'll try some more examples. Okay. So, let's look at this first one here. So we got the limit, t approaches 0, 1 over t minus 1 over t squared plus 1. So you can try to plug in 0, do direct substitution, just like before, but you can quickly see that that's going to make the denominator equal to 0. Okay? And there's really no factoring here. Like I only got 1's on top. I can't really factor t squared plus 1. Like there's no factoring. Okay? So I see two fractions. Let's go with the step where we have to combine two fractions together and see if that kind of helps us with some thought process here. Okay? So if I want to combine two fractions together, remember that you got to get a common denominator. Okay? And in this case, one of those denominators is t, the other one is t squared plus 1. So really my common denominator, I'm just going to say common denominator, is t times t squared plus 1. So I'm going to multiply this side by t squared plus 1 and t squared plus 1, and I'm going to multiply this side by t and t. Okay? So then what I get is the limit t approaches 0 of t squared plus 1 on top of here minus t on top of there, and on bottom we got t times t squared plus 1. Okay? So I guess I should have wrote t squared plus 1 being multiplied on the bottom there. And now we got one fraction. So let's kind of look and see what that does for us there. So I got the limit, t approaches 0. On top, I mean, I can rewrite it as a trinomial if I really want to. I can say t squared minus t plus 1 all over t times t squared plus 1. Okay. Okay, well, that's great and all. I mean, we got down to one fraction. And you can look at the top. It looks like a trinomial, but unfortunately, I don't think that factors. There are no factors of 1 to add up to negative 1. So we're kind of stuck here. Okay? Here's the issue. 0, if I plug it in, makes the denominator equal to 0. And it doesn't, and we're not able to cross it out with anything on top. Even combining it as one fraction didn't help with that. Okay? Well, so it turns out that now 0 is not a whole. So it's a vertical asymptote. By definition, a vertical asymptote is what makes the denominator 0, okay, and does not cross out with anything on top. So vertical asymptote on a graph, okay, let's say it's like, it's right there on a graph. All right, a couple things could happen. Like this side could go up, this side could go down, or vice versa. This side could go up, this side could go down. Okay. Now, in either one of those situations, like the red graph or the blue graph, the vertical asymptote are going to two different spots. So the left and right limit do not match up. So like in this case, left and right do not match up. And if that's the case, then the limit does not exist. Okay, if one's going to positive infinity and one's going to the negative infinity, the left and right limit don't match up, therefore it does not exist. Okay. Or the other situation would be like this. So if I have this as my vertical asymptote, they could both be going to positive infinity, or they could both be going to negative infinity. So in that situation, the limit does exist. Now, the only way that we can do that, like mathematically without a calculator, is we have to test points. We have to test points really, really close to the vertical asymptote and see which direction they're going. Okay? So what I mean is I'm going to write it this way for you. Okay? So we're going to consider the left and right limit. Let's assume we don't have a graphing calculator and we can't just look at it. So I'm going to say the limit as t is approaching 0 from the left, and I'm going to do the limit as t is approaching 0 from the right. Okay, I'm going to do two separate limits here. And then I'll stick with the t squared minus t plus 1 over t squared plus 1. Okay. Now, I'm going to redraw this graph just so you can kind of look at it again. All right, so my vertical asymptote is obviously at 0. So if I'm approaching from the left, okay, that's on the left side here, I need to test a point that is really, really close to my vertical asymptote, but, you know, obviously isn't 0. So I'm going to test a point close enough. I usually go off by like a tenth. So I'm going to test maybe like x equal to negative 0.1. Okay. Now, I have some students that insist on when they're testing these points, they plug in these values that they got to get an exact answer, but I don't necessarily agree with that. All I care about is what the sign is, because if I pick a close enough number to the vertical asymptote, it's either going to be like it's getting closer and closer to negative infinity on one side and positive infinity on the other side. Like if that's the case, if I pick a close enough point, as long as I can figure out the sign, I know which infinity it's heading towards, whether it's positive or negative, if that makes sense. So all I care about is just like what that sign's going to be. So for instance, if I plug negative 0.1 into this equation right here, negative 0.1 squared minus negative 0.1 plus 1. That's going to be a positive plus a positive plus a positive. So I know that it's going to be positive on top, and on bottom it's going to be negative 0.1 times negative 0.1 squared plus 1. So that's going to end up being a negative times a positive, which is a negative on bottom. Okay. So if I have that point is going to be positive or negative, it's going to be a negative number officially, then I know that this value, as I approach from the left, is going to be heading towards negative infinity. Right? And if I were to test on the other side, if I'm coming from the right side of the limit, let's say I'll test positive 0.1. Okay? I'll plug it on top, that's going to be, again, 0.1 squared minus 0.1 plus 1, which ends up equating to a positive number. And on bottom, if I do it again, it's again going to be a positive number. Okay, so in this case, that means we're approaching positive infinity. Okay, so I guess the graph that I drew up here is accurate. It looks something like that. So if that's the case, okay, the left and right limits do not match up, so they are not equal to each other. Therefore, this does not exist. So that's how you approach that. That's how you approach vertical asymptote. You got to do test points. Okay, and unfortunately, that's really the only way we can approach those. Okay. Okay. So this video is getting a little bit long, which is I'm sorry for that. So we're going to save the absolute value problem for class. And if you want to look at the notes and attempt to reason through that, you can. It's not the absolute value problems are not that bad, but I will go over that later. And honestly, I think you can go ahead and do. Oops. I think you can go ahead and do numbers 5 and 6 on your own. Okay, I will go ahead and tell you, 6 is either one of two cases. It's either going to be that the whole, this is a whole and it factors out, or it's a vertical asymptote and you have to do test points. And for number 5 is a complex fraction. So just simplify that out and see if it's either a whole or a vertical asymptote again. Okay, so I think you can try those 2 points. The last thing I want to talk about, and I'll let you pause the video to write this down, but is your notes probably say indefinite. It's supposed to say infinite limits. Okay, that's whenever you have the limit as x is approaching infinity or for a negative infinity, equaling either some number a or positive and negative infinity. So really all I'm talking about here is in behavior. If I'm talking about a limit as x is approaching infinity or negative infinity, I'm asking what's happening at the end of the function to the right or at the end of the function to the left. Okay? And there's rules that you learned about this. And I'll let you pause your video and write these down. But there's polynomial in behavior rules and rational in behavior rules. Okay? So for polynomial rules, it's all about your degree and the coefficient. Your degree of your leading coefficient is either even or odd, so it's like either a cubic function or an odd function or a square function, something like that. And it's either going to be positive or negative. So there's 4 combinations of all those. So an even positive would be like, an example would be like x squared. All right? It's a positive number out front, and it's an even power. The in behavior, you could probably picture, is positive infinity in both directions. You can have even negative, meaning that it's an even power, so like for instance x squared, but negative because it would be negative x squared. So that's an example of that. That flips the graph, and your end behavior is going to be negative infinity on both sides. Okay. You can have odd positive, so that would be like a positive x cubed. On the left side, it's going to be negative infinity. On the right side, it's going to be positive infinity. And you can have an odd negative. And all that does is just flips it. So it's going to be positive infinity on the left side and negative infinity on the right side to infinity. So those are your polynomial rules that you've probably learned in the past, and I want you to kind of hold on to. And then the ones for the rational are all about comparing the highest degree on top to the highest degree on bottom. Okay? The degree of the numerator versus the degree of the denominator. If the numerator and denominator are equal, so like x minus 1 over x plus 1, something like that, then you just take the ratio of the leading coefficients. We'll talk more about that later. If the numerator is less than the denominator, so the denominator has a bigger power, so like for instance, like x over x squared plus 1, then the end behavior, okay, the horizontal asymptote that it's heading to is 0. And if the numerator is greater than the denominator, then you're just going to divide the highest degree, then use polynomial rules. Okay? Then use polynomial rules. So let's look at a couple examples, and I'll let you try something on your own, and we'll finish up for tomorrow. So it says infinite limits. Find the limit for each function. I love it whenever we're given the limit as x is approaching infinity or negative infinity, because it's just in behavior rules, and we're good at those. So if you notice, the highest power on top is 2, the highest power on the bottom is 2. So we're using the ratios of leading coefficients. So there's an understood 1 here. The limit, the end behavior, is just going to be going to 1/3. I'm sure you've done that a lot in the past with end behavior, but there's a little refresher. Okay. And okay, so this is kind of the last slide here. And again, I'm going to try to let y'all do as much as you can here, but it's not too bad. Like for instance, okay, so going to infinity, so it's end behavior rules for rationals. Okay. It looks like the highest power on top is 4, and the highest power on bottom is 1. So if I want to know what's happening like in behavior rules, a simple trick to this is to just divide the highest power on top and the highest power on bottom. So for instance, all I really got to do and worry about is just think about what happens when I do negative x to the fourth divided by x. Okay. So like if I were to do long division here, what's going to happen and all said and done is I'm going to end up getting negative 2x cubed. And I mean, there's going to be more if I divide out the whole function, but that's going to be my leading coefficient. So if I were to divide this out, this means I'm going to get a negative odd polynomial. Okay, so based off my polynomial rule, negative odd means that the end behavior kind of looks like this. Something fancy goes on down here, and then it goes like that. Okay, so as I'm approaching negative infinity, or going to positive infinity, I'm going down negative infinity. So that's kind of what I mean right there. Here in number 3, the powers are the same, so I'm taking the leading coefficients. So that's just 3 over 6, or 1/2. Okay. All right, and again, so here for negative infinity, we go limit to negative infinity. We got a rational, so we're doing rational rules. Think of it this way. On top, you got a power of 1. On bottom, okay, the bottom one is not x to the 4th power, but x to the 4th power and take the square root of that. So really, the highest power on top is x. The highest power on bottom is actually x squared. All right. The numerator is less than the denominator. So that means that this end behavior is 0. Okay. All right. Try number 5 on your own, and we'll go over all the problems we didn't get to in the lesson and answer any questions you have tomorrow. If you want to go ahead and look at your homework, I'm actually going to keep that to 26. 1 through 26 is a worksheet on your online. So good luck. Yeah, try to keep it under 30 minutes, but I'm 2 minutes over. That's okay. Y'all are great.